This is columns part 4. At the end of part 3, we were talking about how this Euler stress equation predicted this column, or this tail boom here, would be 2.6 times stronger than it really was, which pretty much makes the formula useless. Well, I thought it was. However, this is still a very useful formula because it's part of this formula, which accurately predicted how strong this truss was. This formula comes from this website, ASSAKKAF.com, plus a long string of other stuff. It's mentioned in detail in part 3. But anyway, we have this F means stress. It doesn't mean force. It says F, but it means stress. It's the critical stress, the stress that it buckles at. Well, you use either this equation or this one. And you say 0.658 to the lambda c squared. Well, what is lambda c? Well, here it is. It's the square root of Fy over Fe. Well, what is Fy? What is Fe? Well, Fy is the yield stress, typically 36,000 psi. Sometimes it's 50,000 psi. I use 36,000 for mine. And Fe, that's the Euler stress. Another author earlier called it sigma, said sigma equals pi squared modulus of elasticity over KL over R, all in parentheses squared, but this guy calls it Fe. I guess we're just going to have to get used to having different letters pop up all the time for the same old stuff. But anyway, okay, so lambda c is the square root of that over that. Well, that is that. That is that. So let's just put our square root of that over that. Okay, and when we have that divided by all of that, which is that over that, we can just take that and throw it on top. And we can say Fy times that, which is what we did. Fy times KL over R in parentheses squared equals what's left on the bottom, pi squared times the modulus of elasticity. So we have the square root of that. Now we factor out the things that are squared. Well, all that squared is k squared times L squared over R squared. So square root of k squared is k, square root of L squared is L, square root of 1 over R squared is 1 over R, square root of 1 over pi squared is 1 over pi, and we have the square root of Fy over E times all that. That's what our lambda is. Okay. Okay, we learned earlier in this lesson that K, the end condition factor, that K right there, that K, that it's 0.5 for a fixed column, 0.7 for fixed pinned, 1.0 for pinned, and 2.0 for a column with one end free. The author of this website, he uses a, quote, recommended design K of 0.65 for fixed, and instead of 0.5, 0.8 for fixed pin instead of 0.7, 1.0 for pin, which is the same as the original 1.0 that the other guy used, and 2.1 for columns with one end free, 2.1 instead of 2.0. So okay, now we're going to see what these formulas say about the strength of the tail boom mock-up of the steel stork. This tail boom has a top flange, two bottom flanges, and zigzags connecting each other to each flange to the other two flanges. This is the failed component of the tail boom. When the tail boom was tested to destruction, it's about 13 inches long. See, it's U-shaped. See there's the inside of the U where my thumb is. There's the outside of the U, kind of like right here. It's about 7/16 inches across there, and it's 3/8 of an inch from there to there. So it was cut out of a piece of 1/2 inch electrical conduit. here's a sample of that right here. This was ripped in half with a metal cutting blade on a circular saw, and then one of the U pieces that was left was squeezed down to about 1/4 of an inch wide on a 1/4 inch piece of steel. So that's how that came about. So we need to analyze this cross section of our column that failed. Here's how it failed. As you can see, it failed about this axis. If you were to call this the x-axis and this the y-axis, then you could say it failed across the x-axis. If you were to turn it where it looks like a C, then you could say it failed across its vertical axis, but we'll just say it failed about its horizontal axis. As long as you understand that's the way it failed, because its strength about this axis was what was weaker. It's like that I-beam. It's not going to fail in the, if it looks like an I, it's not going to fail in the same direction it would if it looked like an H. So we need to find out what the cross-sectional area of this is, the moment of inertia, the radius of gyration. So here's the end of this pipe. Okay, drawn a little bigger. It's 23/32 in diameter, outside diameter. We'll calculate what the thickness, the wall thickness, and the inside diameter are. Let's swap boards here. Okay. So, okay, a 10-foot section of this pipe, this electrical conduit, 1/2 inch, weighs 3 pounds. Okay, well, a cubic foot of steel weighs 490 pounds. So 10 feet of this, the volume of it, the cross-sectional area there, times 10 feet of length, is equal to that many cubic feet, because it weighs 3 pounds and 1 cubic foot weighs 490 pounds. So 10 feet of this is that many cubic feet, which is that many cubic feet. And we want to turn those cubic feet into cubic inches, so we just multiply 12 inches per foot 3 times in a row, and then we calculate that the volume of our 10-foot section of 1/2 inch electrical conduit is a little over 10.5 cubic inches. Okay, well, the volume is the cross-sectional area times the length. Okay, volume, which is 10.5 cubic inches, equals the cross-sectional area times the length. We know the length is 10 feet, which is 120 inches. So let's figure out what our cross-sectional area is. It's going to equal that divided by that. Volume divided by length. Volume, 10.5, a little more, cubic inches, divided by the length of 10 feet, which is 120 inches, gives us a cross-sectional area of 0.088 blah 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 inches squared. Okay, now let's figure the area of our outside, let's figure the area of our circle here, all the way from the outside diameter. Okay, we need to do that in order to figure our wall thickness, so we can figure our cross-sectional area of our U piece. Okay, the area of this outside diameter, it's going to be, well, it's going to be pi r squared, or pi times diameter squared over 4. The diameter is 23/32 of an inch, so pi times 23/32 squared over 4 equals 0.405 blah 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 square inches. That's the area of all this circle, all this area inside of this outer circle. Okay, now let's figure let's see, we know the area inside is equal to the area outside minus the cross-sectional area. So the area inside is the area outside, which is that, we just figured that out, minus the cross-sectional area, we figured that out a while ago, 0.088. So that minus that gives us our inside area. Let's see. Yeah, that minus that is 0.3175, blah, blah, blah. Okay, so we know our inside area. So let's figure our inside diameter. Okay, it's the same old formula. Diameter, pi times diameter squared over 4 equals area. So we know that, we know that, we know that. This is what we're looking for. So we multiply both sides of this equation by 4. So we have that times 4. That times 4. We divide each side of the equation by pi. So there's our pi underneath. We take the square root of each side so we can get just plain old inside diameter instead of inside diameter squared. And we have inside diameter equals square root of all that. We crunch the numbers and we get this number, 0.63588. Okay, so that's our inside diameter. We know our outside diameter minus our inside diameter equals the thickness of that wall plus the thickness of that wall. So one wall thickness equals outside diameter minus inside diameter divided by 2. So outside diameter minus inside diameter divided by 2 equals 0.0414, or 41 thousandths of an inch is our wall thickness. There we go. Now that we know the wall thickness of our U-shaped beam or column, we need to find out what our length is here. My best estimation is that it's 0.921875 inches from here to here. The way I arrived at that is I put a piece of paper inside here and bent it at the corners. And then I put another piece of paper on the outside of it and bent it at the corners. And those two sheets of paper, one of them was 13/16 inch long, the one on the inside of the U. The one on the outside of the U was 1 1/32 inch long. So I just average these two. That plus that over 2 gives us that. So our cross-sectional area is the length of our U times the thickness of our U, which is 0.921875 times 0.0414 blah blah blah, giving us a cross-sectional area of 0.038 square inches.